Hello Prom and Ping An, this is especially for you. We've stopped doing practical work and we're doing some theory, looking at topic 7, which is called equilibrium. So the first question is, what is meant by the term dynamic equilibrium? Now, this will be interesting to you. If you speak loudly enough, will it record your answer?
Okay, I think that equilibrium means the equilibrium, that balancing the product and the reaction.
Okay, it's to do with balance. Yes, that's what equilibrium tends to mean. But there's a bit more to it. Okay. When you reach a state of dynamic equilibrium, it means the forward and the backward reaction are occurring at exactly the same rate. Now, I should add that this applies to reversible reactions, and a reversible reaction is a reaction in which the products can react again to form the reactants. It's called dynamic because the forward and the backward reactions, the forward reaction is the reaction from left to right, backward reaction right to left, both occurring at the same rate. Now, there's one other thing it has to be, or there's one other condition for, that's right, Evie, it has to be in a closed system. Okay, otherwise it wouldn't reach equilibrium. So, I want you to imagine you're in the Brunswick Centre. Okay, you've got an up escalator, no, that must be a down escalator. You're running up it. To stay in the same place, the position of equilibrium, you must be going at exactly the same speed as the escalator. Same with equilibrium. Both reactions occurring at exactly the same rate, forward and backward. Now there's a special symbol used, which I'm sure you've all seen before. If you haven't, there it is. Key thing to notice is that they are not proper arrows. They're sort of half-headed arrows. So, why is that picture misleading? It's a person, not chemicals, yeah. Sorry? Okay, this suggests you're bang in the middle here, but that doesn't have to be the case. You could be down here at a state of dynamic equilibrium. You could be up there in a state of dynamic equilibrium. So the picture's misleading, it suggests it's bang in the middle, the position of equilibrium. It isn't. So there are some better pictures, and actually linking to chemicals this time. Okay, you've got the person running up, and the escalator running down or going down in both pictures. But you can have a position where there are more reactants than products, and you can have a position where there are more products than reactants. For an equilibrium, it doesn't matter whether you start with the products or the reactants when you start it off. So that's a better picture there, and as you can see, it's linked it into chemicals. So, here's a little illustration of the sort of thing that can potentially happen. This is a plot of rate of reaction, which we're experts on, against time for an equilibrium. If I start with hydrogen and iodine, you can see that the rate decreases. Simultaneously, the rate of the reverse reaction increases until we get to this position here. And that's the position of equilibrium, starts there, keeps going on and on and on, a bit like I do, and the concentration of the reactants and products remain constant. They are not the same as each other, because if they were the same as each other, it would be the position in the middle that we saw on the first escalator. But you can have more reactants than products, and vice versa. Okay, there's no apparent change occurring. You cannot see any change. If I was to get you a bottle of orange potassium dichromate, there's an equilibrium set up in there between the orange dichromate ion and a yellow chromate ion. There's a few illustrations on the internet that will show you that. It always appears orange, even though that reverse reaction is continuing. Orange is a stronger colour than yellow. Okay, so here's the important bit that's beyond GCSE now. Something called the equilibrium constant. The equilibrium constant gives us a measure of whether we've got more reactants or more products. A high value means that we've got more products. A low value means that we have more reactants. Remember, Prom and Ping An, you can pause this video whenever you want to make sure that you write any bits and pieces down that you want to. So, how do we write an expression for Kc? Well, to write an expression for Kc, we have to make sure that all the reactants and products are in the same phase. Remember, phase is just a fancy word for state. So that means we can only write them for homogeneous equilibria. And Kc is expressed in terms of the concentrations in moles per decimeter cubed of the reactants and the products. And you can only work out an expression for Kc from a balanced chemical equation. And I've got a very creative equation there. It took me ages to come up with that, and we'll see on the next slide how that converts to an expression for Kc. So, the equilibrium constant Kc is given by the products concentrations raised to the power of the little number you get in front of them, the big number you get in front of them in the equation. Multiplied together, please, not added. Divided by the reactants. Again, raised to the concentration.
What's going to be for Kc? What's that going to be? The number of the
concentration in moles per decimeter cubed.
Okay. How much?
Concentration moles per decimeter cubed.
Okay.
We'll see a couple of examples in a minute. So now, the other thing, a little bit controversial this, the units for Kc are never the same. There's deliberately noises off here, I'm sure. They always have to be derived from the specific expression for Kc. Now it's controversial because technically these aren't concentrations. And if you go and read chemistry at degree level, they'll tell you that there's something called activity values for C, D, A and B, rather than concentrations. And activities have no units. But we'll keep it basic and we stick at having units. So let's have a look at an example. So, how do we start with that? Well, we simply write Kc equals. It's as easy as that. But what does it equal? Okay, products divided by reactants. Anything else going in there, Jude?
Let me. Sodium and sulfur.
Where's sodium?
No, sulfur. Sulfur oxide.
Sulfur trioxide.
Yeah, it's going to be the same box, same bracket.
In one bracket, yeah. What's going to be outside that bracket?
2.
Yes, a squared, because it's 2 in front.
Okay.
So that's the top bit sorted.
Mm-hmm.
What's going to be on the bottom then? Come on, Toulouse, we need to hear your voice on this video. Just in square brackets, yep. And there we are. That's what you get.
What number will be? Number SO3.
Squared.
What should be the number of the SO3 concentration?
What's the number?
Yeah.
We don't know, we haven't asked that question yet.
Oh.
That's later.
Oh.
Later I will give you some numbers and all you have to do is put them in the equation, square them or whatever, and you get the answer. Max? It has to be square brackets. If you put curved brackets, it will be marked wrong in the exam. Because square brackets mean concentration, curved brackets mean nothing. Now, how do we determine the units for that?
Mole.
Well, that's moles per decimeter cubed. It's squared, so on the top it's moles per decimeter cubed times moles per decimeter cubed.
Mole square.
Which is moles squared dm to the minus 6.
Oh.
On the bottom, we've got, you can work that out, moles squared dm to the minus 6 again. One extra lot here for the oxygen of moles per decimeter cubed. So if you're a strong mathematician, you can, or even I can, you can cancel the moles squared dm to the minus 6, and you're left with 1 over moles per decimeter cubed. Yeah? How do I get moles per decimeter cubed times moles per decimeter cubed is moles squared per decimeter to the minus 6.
Oh, so that's why it is 1 over.
Oh, could that be why you got the hint of needing 1 over equals? Yes. There we go. So you've effectively got 1 over moles per decimeter cubed, 1 over concentration, which is moles to the minus 1, dm to the 3.
Is it the unit always the same, or is it going to be like more?
No, I've already said the units vary.
Okay.
So, you could try this one yourself and see what the units are. Pause the video while you work out the answer to number 2. So, number 2, the solution is Kc equals NH3 in square brackets raised to the power of 2 over H2 in square brackets to the power of 3 times the N2 concentration in square brackets with no power. So the units you should get at the end of that are 1 over moles squared decimeters to the minus 6. Take that to the top and you get moles to the minus 2 dm to the 6. Okay, I'm just about to put the worksheet entitled Kc and its units on Google Classroom for you. Have a try of that. Then please scan your answers and send them to me.